Okay, this is the second in our series of lectures on chemistry 121, organic chemistry 1. We had started by looking at the starts of the field of organic chemistry. In order to help us with a better understanding of organic chemistry at this basic level, we had to do a review of atomic structure, electron configuration, bonding, and so on and so forth. Today we want to move a little bit deeper by looking at bonding in carbon that results in the diversity of structures and also the number of organic compounds that have been reported. At the end of the lecture today, you should be able to explain the meaning of hybrid orbitals. You should define hybridization and explain it. And explain bonding in and structure of methane, the simplest hydrocarbon. Explain sp2 hybridization as well as sp hybridization of carbon, and of course discuss the structural peculiarities that arise because of that hybridization. And then we want to be able to draw structure of these organic compounds, understand the various formats in which this can be presented. So, to discuss hybrid orbitals, let's take a look at methane. Methane is a simple organic compound that consists of one carbon atom bonded to 4 hydrogen atoms as in that structure. Now we notice that all bond lengths and bond angles in methane are the same. But if you recall that the valence electron configuration of methane is 2s2 2p2. It means we have one s orbital and 2 p orbitals. And that should be, and the s orbital, as we discussed, is spherical, whereas the p orbital is directional in dumbbell shape. And so if these orbitals were to be involved in the bonding, we don't expect that all the bond length and angles should be the same because we're using different orbitals for that purpose. So, but it turns out that methane formed 4 bonds. The bonds are all equal, all the same. So if methane formed 4 bonds using valence electrons, and all those 4 bonds in methane are the same, then it means that the 4 orbitals responsible for the bonds in methane must be the same. Let me repeat that. We're using 2s, spherically symmetrical, and 2p orbitals, 2 of those that are dumbbell shaped and they are directional. And so if you have 2 different orbitals, then they should be forming 2 different kinds of bonds. That means that in methane, we should have seen 2 different bond lengths and 2 different bond angles. But it turns out that all the bonds in methane are the same. If that is the case, then it means that something happened such that the orbitals involved in that bonding are the same. And that's what we'll talk about. That brings us to the principle of hybridization. So we look at the orbital picture. Here we have a 1s, which is 2 electrons in the core, and then we have 2s orbital having 2 electrons, and 2p having these unpaired electrons. Okay? So hybridization shows that, or means that the 2s orbital and the 2p orbitals in a valence shell all combine to form 4 sp3 hybrid orbitals. Remember, there is 1, 2, 3. The p orbitals are 3. We have a 2s, which is 1 orbital. So you combine 1 plus 3, and that gives us sp3. 1s with 3 p's. That's how we get sp3, hybrid orbitals. What do we mean by that, hybrid? The hybrid orbital means that the orbital we create is neither an s nor a p. Neither s or p, but some combination thereof. It's just like a black person marrying a white person and they have a baby. That baby is neither white nor black, but is a hybrid of those two. So when you combine an s and 3 p orbitals, you get 4 orbitals that now have a new identity, neither an s nor a p. So these are formed by hybridizing. That's the word used, and this was formulated by Linus Pauling in the 1950s. So when carbon atoms bond to form 4 other atoms, the 2s orbital, there is 1 of them, and 3 of the 2p orbitals in the valence shell combine to produce 4 sp3 hybrid orbitals. Okay? And this is what we're looking at here pictorially. So you have the 2s and then the 3 p orbitals. They combine, and you can see that this is now the shape of the hybrid orbital. So you can see this shape here, neither this nor this, it has its own different identity. Or we can show here that instead of the 2s just sitting there and then the 2p up there a little bit in energy, one of these electrons is promoted, and then we have 4 hybrid orbitals. This is also promoted, all of them occupying the same energy level. Okay, so the sp3 hybrid orbitals, when they form around carbon, will now have a relationship and an effect on the shape of that molecule. So in the case of methane, where this is hydrogen, 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 there is a central carbon. And mind you that this, what we have here as a line, represents 2 electrons that have come together in that sharing. Remember, we talked about covalent bonds, and we have shared electrons. So there are 2 electrons in this bond, 2, 2, 2. And the electrons are negatively charged. So they want to stay as far apart as they can, because 2 negative charges will repel each other. And it turns out that the best structural disposition of those bonds is such that the carbon will be at the center of a regular tetrahedron, and that the angle between one bond and the other is 109.5 degrees. 109.5, 109.5, 109.5. And this is how we represent it. We represent it. Something else I want you to pay attention to. So here, you can see that we have hashed lines, okay? And here we have a solid wedge. And then we have 2 of these lines, just a regular line. Again, I repeat, this one is hashed, this one is solid. And this thing is supposed to indicate a bond. Here, if you can imagine that this is a plane, okay? So this bond and this bond are in the plane of this wall. When we use a hash line, it shows a bond that is pointing behind. And this one, okay, with the solid wedge, shows a point that is pointing out towards us. And that is what is just a way to represent a 3-dimensional structure. 3-dimensional structure means that this thing is a plane, it has depths inside and outside. So we have an X, Y, and Z dimensions. Alright? Now, so that takes care of sp3 hybridization leading to single bonds. Now, it can also be a hybridization where the 2s orbital hybridizes with 2p orbitals. Remember that there are three of those 2p orbitals, but it only hybridizes 2 of them. And this results in the formation of 3 sp2 hybrid orbitals. Remember, 1 s and 2 p's. And this gives us orbitals of equivalent energy. So there are 3 of them. So you can imagine that this one is promoted there, but only 3 of those are hybridized to form 3 sp2 hybrid orbitals. And so we have it 2s, and those 3 p orbitals we designate as px, py, and pz. Okay? So in that hybridization, we take a 2s, 2px, 2py. 2pz is unhybridized. And what happens then is that you have a trigonal, because the way to arrange themselves, to remember, the electrons want to be as far apart as possible. And so in this case of 3 orbitals, they're staying as far apart as possible, and each at about between them an angle of 120 degrees. So the 3 orbitals are in the same plane and now creates a top and a bottom. They are at an angle of 120 degrees to each other. Now, remember that there is unhybridized P. So we have, okay, so here I have 2px, well, it could be also the 2pz on the 2 carbons now that are forming the simplest sp2 compound, and that is ethene. We shall come to that later. So if you can imagine that this has those 3 orbitals. So one of them is used to form a bond, sp2 hybrid orbital. So one carbon brings its own sp2, the other carbon brings its own sp2, and they form that bond. And then the other sp2, remember there are 3 of them, it's used to form a bond to hydrogen, and then another one to hydrogen. The same thing happens with this carbon, hydrogen, and hydrogen. And now you have the p orbital, let's call it the pz, that is not hybridized, and at 90-degree angle to this. So you can imagine assuming that it is actually projecting out of the page. So something that has depth, as we said. So half of it is on this side, half of it is on the other side. And so now we can have, instead of the orbitals here overlapping head to head, we have them overlapping side to side. So basically, instead of joining like this, they are all standing parallel, and that interaction can occur between them. So we call that a parallel overlap instead of a head-to-head overlap. This is a head-to-head overlap resulting in a sigma bond, whereas a side-to-side overlap, as we have here, results in what we call a pi bond. So you can see, remember that sp2, they're in the same plane, and then above and below is where we have the loads of these orbitals. So they overlap above and below the plane of that, resulting in what we call a pi bond. Now, the other type of bonding in carbon is sp hybridization, and this results in what we call a triple bond. So here you have 2 sp hybrid orbitals resulting from the hybridization of a 2s orbital with only one 2p orbital. So we can say we use 2px, 2py and 2pz are unaffected, not hybridized. And you can see that depiction here. And so you use those 2 hybrid orbitals to form sigma bonds. And then the carbon overlap to form 2 pi bonds that are 90 degrees to each other. This is what it looks like. So basically, we have talked about the single bond, the double bond, and now the triple bond. So you have sp hybrid orbitals, two of them. So one of them is used to form this sigma bond. From these carbons, one sigma bond, and then the other one is used to form a sigma bond, let's say with hydrogen. And then you have an unhybridized in one plane, another one is in that plane. So we're looking at something like one is going in, out, and then the other one is up, down. So we can have two regions of overlap leading to a triple bond. And this is just pictorially showing where you have that electron density between the two carbons, all the overlap of the triple bond, and then you're showing the sigma bond to those hydrogens. Okay? Now, so let's just summarize what we have here. Because from what we've already discussed, covalent bonds are formed as a result of overlap of atomic orbitals. And the atomic orbitals results when they combine to be molecular orbitals. There are two ways in which these orbitals can overlap. Head-to-head overlap of orbital results in what we call sigma bonds, whereas side-to-side overlap results in what we term pi bonds. So you can see two s orbitals overlapping, two p orbitals overlapping, or one s and one p orbital overlapping. Okay? So the bonding electrons in the sigma bond are located along an imaginary line joining the nuclei of the two atoms. So if this is the nucleus of this is the nucleus of that other, then the bonding electrons are found somewhere, the sigma bond in between, an imaginary line which is between this nucleus and that nucleus. And in the case of pi bond, we've already talked about the overlap above and below the plane of the bond. Just to note that pi bond is a weak bond, is weaker than sigma bond, because whereas the sigma bond is found between the nuclei which hold them together, pi bonds are kind of projecting out. And this thing has implications for the types of reactions that they would undergo. And that's something we will delve into when we get to CHM 212, the higher level. So, and we can depict, for example, this double bond here as showing two regions of those electrons overlapping above and below the plane of the bond. Okay, so now that we've seen how single bonds, double bonds, triple bonds arise, we need to look at carbon atoms then, because we said they form a large number of compounds that come together in series. So it's capable of forming single, double, and triple bonds with other atoms. And these bonding patterns are adequately described by the model that uses overlap of atomic orbitals. Let's take ethane, okay, which again we are going to talk about C2H6, has two it has a carbon to carbon bond, two carbon atoms, and then it has 6 hydrogens. Okay, the bonds here arise from the overlap of orbitals on adjacent atoms. So end-to-end overlap of sp3 orbitals produces a sigma bond. All single bonds are sigma bonds. Remember, all single bonds are sigma bonds. And it allows for free rotation around the single bond. Okay? So each carbon in a ethane molecule, which is the CH3CH3, is sp3 hybridized and tetrahedral in shape. Remember, we talked about an angle of 109.5 degrees, and we talked here also of free rotation, which means that there is free rotation between the carbon-carbon single bond. Okay? So each carbon atom can form 4 bonds, either to other carbon atoms or to different atoms, such as hydrogen, oxygen, nitrogen, sulfur, phosphorus, fluorine. And we can show what happens as here. Sorry, I think one of the dots is missing. There should be a dot there, and there should be another dot there. Okay, so this has a little bit of a problem. But anyway, the dot here combines with that dot to form that. And we should be left with 3 dots around them. One of them having been used to combine with the other one, overlap to form to give that sigma bond. So we represent that with a line. In other words, we have 2 electrons. 1 dot here, 1 dot here. They combine to form a bond. That bond we represent with a line. So if you remember that 2 electrons combine to form that bond, then remember that this line here, this bond here means 2 electrons. Okay? Now, another carbon can combine, make 3, another one, 4, and so on and so forth. And so when that happens, we can see we have 1, 2, 3 bonds, and then the carbon still have, like here, has 3 electrons. This one has 2, and this has 2, and this should be actually 3. So there is further possibility of extending that structure. In the case of double bonds, we have 1 here and 1 here forming that double bond, as we saw in the case of ethane. And then this carbon still has 1 electron that it can use to form another bond. Now, you go to the case of the triple bond. So the carbon here has 3 bonds to this carbon, a single bond to that, and then this has also 1, 2, 3. Something to remember if you forget everything we've talked in this particular video, is that the number of bonds to carbon cannot be more than 4. So if you look at this carbon, we can count 1, 2, 3, and this one 4. For this one is 1, 2, 3, and then this one 4. For this carbon, this is 1, and then this will make another bond, 2, 3, 4. Here we have 1, 2, 3, and then this one 4. If you ever write 5 bonds to a carbon, that is a no-no. Is a chemical equivalent of religious heresy. You don't do that. It's chemical heresy. You can't have more than 4 bonds to carbon. Remember that. So, you've seen how we can represent these bonds or those electrons bonding with a line. So, in order to make our lives a little easier, we don't have to be putting out all the bonding and so on. We come to some agreement as to what should represent an organic compound. How do we represent these organic compounds? So we can have an expanded structural formula. So for example, this one is C2H6. So you can see 1, 2, C2. So that means we have 2 carbon atoms. And we have the C, capital C, subscript 2. And all that is saying is that there are 2 carbon atoms. And then we put H and also subscript 6. In other words, look, count. 1, 2. That's 2 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6. And we write it as such. Now look at what I have written. I've written C2H6, capital C, subscript 2, capital H, subscript 6. I didn't write C2H6. It's unacceptable. And this is the way that chemists have agreed to write it this way. It is not up to you to change it. And until we all meet and agree that we are going to write it this way, please stick to what the International Union of Pure and Applied Chemists have agreed. That's the standard. And the way we do that, the reason is that somebody anywhere reading the structure you have put down or looking at the formula you have put down understands what exactly you meant to say. If you put something like this, there might be a disagreement, okay, as to what it is you're portraying. So that's C2H6. Here we have a double bond, and that's how we represent it. And this one will be C1, 2, 3, C3. How many hydrogens there? We count 1, 2, 3, 4, 5, 6. C3H6. All right? Now, what did we say about the structure? So here there is a double bond. So if we count the bonds around this carbon, that will be 1, 2, 3, 4, never exceeding 4. Around this 1, 2, 3, 4. Around this one 1, 2, 3, 4. Okay? Now, we can have different arrangements of the atoms there in the bonding, and you can see here we have 1, 2, that's C2, 2 carbons, hydrogen, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, H6, and then there is 1 oxygen. So carbon first, hydrogen, and then the other elements. Okay? Alright. So, now suppose I want to write the structure of that ethane. I'm teaching a class. You know, you think I should be each time doing this? It's going to take me a long time to be putting up that structure. So then, if we agree, we can, have other ways of representing this thing that makes it a lot easier on all of us. And so, chemists agree that, if I have C, H, 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 we can as well call it CH3. Okay? And then this one is CH3. So, we can do this CH3. And you see that that's faster. So we represent this compound as CH3 or dash CH3. I can write this CH3 or H3C, like it doesn't matter. It doesn't matter. Okay? So, but, you might be asking, why all of this? It's just to simplify it for us and make things move a little faster. We don't spend the whole time writing, structure. As long as we agree that that's what it is, then that's fine. What is important is what we agree that structure represents. So, for example, imagine, in Hausa, Zo. I hope that's the spelling. Zo in Hausa means come. And that's what we agree. Whenever you hear that language and you understand Hausa, it means come. But suppose you never met an Hausa person all your life. Zo means nothing. It's just a sound. So, what is important is what value we attach to that or what it represents. As long as we agree that this is what it represents, then all of us can interpret that the same way and there will be no confusion. So we can even reduce this further, as you see here. Instead of CH3 bond CH3, we can just write CH3, CH3. As long as we agree that once it's put this way, it also represents that bond between them. Okay? So we have this expanded structure where we show everything. We have the condensed structure where we begin to reduce it to this way so that it's easy, quicker to write. And so, for example, you have this, by the way, this is ethanol, okay? And you can see CH3 or H3C dash CH2OH. And we can just put all of that CH3 CH2OH. Okay? All right. So that's the way to represent that structure. So now, we can also represent this thing in terms of line drawing. Again, simplification of that structure. So, here, we have CH3, CH2. And all we do is just represent that with a line. As long as we agree that when we put a line like this, what is at the end is a C. So here, for example, we put that straight line. This will be a C joining another C. And each of those C's will have 4 bonds around them. We agree that those bonds, for in this case, if we don't show anything else, that this thing here will have to carry 3 hydrogens. So we agree on that. So in the case of ethene, we do something like this. Again, any end here is carbon. So if you put a carbon here, we'll put a carbon here, we'll put a carbon here. Each of those carbons has to have 4 bonds. And unless we indicate any other atom there, if we don't indicate, then we all agree that that thing has to be hydrogen. So I can go in and put an H here, put an H here to make it 1, 2, 3, 4. Put another H here to make it 1, 2, 3, 4. And then for here, I'll have to have 3 of those hydrogen. Okay? So, in this particular case, you're looking at the expanded structure. Okay, no, before I say that, let's also even go here to that alcohol. Now, because this one involves an element other than carbon and hydrogen, then we have to show that. If it's fluorine, we have to show that. But for carbon and hydrogen, we can just render them as line. So this here will be CH3, CH2, OH. And this one will be CH3, CH2, O, CH2, CH3. Look at this expanded structure. We have carbon 1, 2, 3, 4. And all the others are hydrogens. And so the line drawing here will just be this zigzag. So this is a carbon 1, 2, 3, 4. So it's representing this expanded structure, condensed structure, line structure. Okay? So, now, suppose I draw something like this, which I can give you on the exam. So, we have something like this, okay? Then here, and then here, here. And I ask you to write the condensed structure or the expanded structure. So you should know that this is a CH3 here, because you have to make up the 4 bonds, hydrogen, hydrogen, hydrogen. This one is another carbon, but now it has 1, 2, 3, 4, so there can't be any hydrogen attached to it at that point. Now this carbon here has 1, 2, 3. Then that means there has to be 1 hydrogen. And this one has H, so it has just this line here, then it has to be CH3. This one, 1, 2, there must be 2 hydrogens here and there. So I can have the structure looking like this: CH3, for this. And then I can have this bond here, C, CH3, CH3. And then here will be CH, CH3, CH2. Okay, let me put it the same way so that it's not confusing. So this is H, CH2, CH3. It's that simple. Each of those carbons will have to have 4 bonds to them to do the line drawing. Okay? So, here you have some examples. Either to do the expanded structure or line structure. I want you to go ahead and practice on this, okay? You know, maybe I should just do the first one for you as an example. So, all right. So if we are looking at this, for example, we will call that, you know, a condensed structure. Okay? So, if you want to write the expanded structure of that, I see that there is a carbon there. Alright? And there are 3 hydrogens. So, I'll put hydrogen. I hope you can see this. Hydrogen, hydrogen, hydrogen. That's the CH3. And then the next one is carbon, 2 hydrogens. Hydrogen, carbon, hydrogen, hydrogen. That's for the second one. The third one is carbon, hydrogen, hydrogen. The second one, carbon, hydrogen. Now you see the CH3 in parentheses because that one is actually bonded to that carbon. So I put this CH, H, H. Now this thing I can put it up and put this H down, it doesn't matter. And then that one is attached again to a C, H, H, and then to a C, H, sorry, H, H, H. Alright? When I do this, I always want to go back and count and make sure that I have the number of carbons represented, I haven't lost any, and I haven't added more than that. So if I go over here, I have 1, 2, 3, 4, 5, 6, 7. And here I have 1, 2, 3, 4, 5, 6, 7. The first one is the CH3, which is this. The second one is the CH2, which is CHHCH2. The next one is the CH2, CHHCH2. The next one is a CH, to which is then attached another CH3, C123. And then that other first carbon is attached to CH2 and then to a CH3. This should be easy to do, not complicated. Okay? Now, just as you go on to do your the look at this close look, we kind of condense this thing again. So CH3 here, so CH3, and then CH2, all of that in bracket 3, CH3. It's just the same thing as CH3, CH2, 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 CH3. In other words, instead of writing this thing, we put all those CH2s, there are just 3 of them. 1, 2, 3. Put that in bracket and further condense that structure. Okay? So, just to round up, of course, you need to practice writing out the condensed structure, the other ones, the line structure, the expanded structure. So in this class, we've talked about bonding in carbon. We talked about sp3 hybridization that results in all single bonds. We talked about sp2 hybridization that results in double bonds, and sp hybridization that result in triple bonds. And we've seen how the carbon atoms combine to give us single bonded compound, doubly bonded compound, triply bonded compounds, and how we can write the structures of this either as the expanded structure, the condensed structure, or the line structure. So this gives us a general overview of organic compounds, carbon compounds bonding in carbon. We are now going to move on to pick individual classes and start examining them much more closely in subsequent classes. Thank you for your attention.